Physics Part 391. We've got section questions. Question number 1. The table below shows the variation with time t of the activity of a sample of a radioactive nuclide X. The average background count during the experiment was 36 minutes. Well, TR activity per minute. 0854 1752 2688 3576 4544 5486 6448 7396 8362 9334 10284. Number A. Plot a graph to show the variation with time of the corrected count rate. B. Use the graph to determine the half-life of the nuclide X. Question number 2. A radioactive source with a half-life of 10 days has an initial activity of 2.0 into 10 power raised to 10 BQ. Calculate the activity of this source after 30 days. The half-lives of two radioactive nuclide X and Y are 40s and 70s respectively. Initially, samples of each contain 2.0 into 10 power raised to 7 undecayed nuclei. A. Calculate the initial activity of each sample. B. Draw on the same axis two lines to represent the decay of these samples. Question number 4. Calculate the mass of cesium 137 that has an activity of 4.0 into 10 power raised to 5 BQ. 0.137 kilogram of cesium 137 contains 6.0 into 10 power raised to 23 atoms. The half-life of cesium 137 is 30 years. 5a. The activity of radioactive source X falls from 5.0 into 10 power raised to 10 BQ to 1.0 into 10 power raised to 10 by 10 BQ in 5 hours. Calculate the half-life. 5b. The activity of a certain mass of carbon-14 is 5.00 into 10 power raised to 9 BQ. The half-life of the carbon-14 is 5570 years, 5570 years. Calculate the number of carbon-14 nuclei in the sample. Next section is 13.7 mass defect. At the end of this section and the following sections, in fact 4 sections, 13.7 to 13.11, you should be able to show an appreciation of the association between energy and mass as represented by E is equal to mc square and recall and solve problems using this relationship. You should be able to sketch the variation binding energy per nucleon with the nucleon number. You should be able to explain the relevance of binding energy per nucleon to nuclear fusion and nuclear fission. At a nuclear level, the masses we deal with are so small that it would be very clumsy to measure them in kilograms. Instead, we measure the mass of a nuclei in nucleons in atomic mass units U. One atomic mass unit 1U is defined as being equal to 1/12 of a mass of a carbon-12 atom. 1U is equal to 1.66 into 10 power raised to 27 kilogram. Using this scale of measurement to 6 decimal places, we have proton mass MP 1.007276 U